has a level curve which passes through this point, which would be a circle going like this. The levels will be parallel to the floor, right? So the level will be, it's just going to be the plane which is parallel to the floor, which goes to this point. It will cut the paraboloid over a circle. It will make a circle out of the paraboloid. And therefore, we will get a curve on the graph, this circle. Okay? Now, this plane touches the whole graph, and in particular, it touches the level curve. But inside this plane, I will have a line which is specifically tangent to the level curve. So this is a tangent line to the level curve. You see what I mean? On this picture, I drew this tangent line downstairs because the other thing I did is I dropped the level curve onto the xy plane, and then I drew the tangent line, this tangent line. But now let me draw this tangent line right here. So this white tangent line is that tangent line over there. Okay? I hope this makes sense. Okay. But now the point is that this tangent line belongs to the tangent plane. You see that there are two tangent things. There is a tangent plane to the whole graph, and there is a tangent line to just the level curve. But the level curve is part of the graph, so its tangent line has to be part of the tangent thing to everything, which is the tangent plane. That's why I drew that line. I drew that line on this tangent plane. And now let's talk about normals. The normal vector to the entire tangent plane we discussed last time, or whatever, 2 weeks ago. And that's the vector which has f sub x, f sub y, and negative 1, right? When we use that normal vector to write down the equation of the tangent plane, which was like z minus z0 is equal to fx, and so on, right? So this we knew from before. That's the normal vector. But now I want to talk about the normal vector to just the tangent line to the level curve, which is not the same thing, you see, because this vector has 3 components, because it's a normal vector to a plane in space, right? It has 3 components. But now I want to talk about the normal vector to the curve. And again, this curve can be thought of it has sort of 2 different incarnations. One is the curve which lives on the graph itself, so it sort of lives, it's elevated over the xy plane, and then there is this tangent line. So really, this tangent line, my picture is terrible because this two have to parallel, of course, right? My worst drawing so far. Imagine that these two are parallel, okay? Looks like non-Euclidean geometry. Parallel lines intersect. They shouldn't. So, but anyway, I don't want to waste more time redrawing. So let's just trust my word. They are parallel to each other, okay? Even though it doesn't look this way. So I think the most confusing aspect of this whole story, the story is incredibly elementary, but the reason I'm explaining to you because in my experience, many people find this confusing. And I think the main reason why people find it confusing is because there are 2 ways to think about the level curve. One is to think about the level curve as being part of the graph, which in some sense is a right way because that's how it was defined. It was defined by intersecting the graph with the plane. But then we realize that once you do that, the z variable effectively disappears. So we might as well think of it as a curve on the xy plane. Even better, let's think of this plane as being the xy plane. And then actually we don't have to move it back and forth. Just think of this as being a plane with 2 coordinates x and y and no z coordinate. Okay? So as such, this curve has a tangent line. Okay? And the question is, what is the equation of this tangent line? That's what I'm getting at. So the equation of the tangent line, we can obtain very easily from the equation of the tangent plane. Because let me remind you, the equation for the tangent plane. The equation for the tangent plane is like this: z minus z0 is equal to f sub x, x0 y0 times x minus x0 plus f sub y. Right? That's the equation, which we have discussed many times and it was even on the meter. Right? And of course, saying that that's the equation of the tangent plane is precisely saying that this is a normal vector, right? Because these are the components, f sub x, f sub y, and negative 1. Why negative 1? Because if you take this to the right-hand side, you will see that z minus z0 appears with coefficient negative 1. Right? So that's this negative 1. This negative 1 is here because we have this term z minus z0. Okay, so that's the equation of the tangent plane. And now I would like to write down the equation for the tangent line to the level curve inside this plane. What should I do for this? Well, on the level curve, z is equal to z0. And that's the definition of the level curve. So on the level curve, z is just identically equal to z0. Everywhere on this level curve, z is equal to z0. Right? So this has to drop out. This has to disappear. And then we'll get the equation of the part which is tangent to just the level curve. So therefore, the equation of the tangent line to the level curve is f sub x of x0 y0 times x minus x0 plus f sub y of x0 y0 times y minus y0 is 0. That's the equation of the tangent. So let me remind you that these are numbers, right? These are the numbers, 2 numbers. And these are the variables. So we have x minus x0, y minus y0. And what are these 2 numbers? These 2 numbers are precisely the components of the gradient vector. In other words, you see, in the equation of the tangent plane, we have the 2 partial derivatives. But we also have this negative 1, which comes because of this term, z minus z0. Right? But once we look, when we focus on the level curve, this z minus z0 disappears. So the only information which is left is the 2 partial derivatives, fx and fy. And we get the equation for the tangent line to this level curve. Okay? Any questions about this? Yes? That's right. It's on the xy plane. Exactly. So I want to do the analysis of everything related to the level curve on the xy plane. Strictly speaking, each time I would have to add the equation z equals z0 to indicate that actually this plane is elevated to that level z0. But usually we don't do that. We just kind of skip that. Okay? But this has to be understood. You either have to think that you're here, but then each time you have to add the equation z equals z0, or you could just say, okay, we're just thinking about dropping everything onto the xy plane. Okay? But now this equation is very suggestive because this equation is just like the equations of planes that we're used to writing, right? So I claim that this equation precisely means that this is a normal vector to this line. So, therefore, is the normal vector to the tangent line, to this tangent line, which is illustrated by this picture. This yellow vector is the gradient vector, this is a gradient vector. Right? It is perpendicular to the tangent line, or normal to the tangent line. But to say normal to the tangent line is the same as saying normal to the curve itself, right? We don't distinguish between being normal to the curve and being normal to the tangent line. It's the same thing. Because it's something about just a very small neighborhood, so linear approximation is good enough for this. Why is that normal vector? That's actually something we should have talked about before, but we didn't. So this is sort of a digression. What is the general equation of a line on the plane? So actually, let me do it as a kind of analogy. Okay. So here we'll look at planes in R3, and here we will talk about lines in R2. What is the equation? What is the general equation of a plane in R3? This we know very well. A x minus x0 plus b y minus y0 plus c z minus z0 equals 0. Okay. Let me emphasize this a, b, and c. What are these a, b, and c? A, b, and c are components of the normal vector. Normal vector to this plane. Okay. For a good reason, which we explained, when we talked about planes. Now I want to express lines in R2 in the same way. And I claim that a general line in R2 can be written exactly the same way, except I don't have the last term, because there's no z. So a times x minus x0 plus b times y minus y0 equals 0. I claim that just like this is an equation of a plane in R3, this is an equation of a line in R2. For the same reason. It's actually simpler, because it's a line in two-dimensional space as opposed to a plane. But we never talked about this somehow. Because well, usually we talk about lines as given by equation y equals kx plus b or something. But actually that's not the most general equation, because what if you don't have a coefficient in front of y? What if you have it doesn't take care of the vertical lines? So this is the most general formula for a line in R2, which allows vertical, horizontal lines, whatever. And of course, if you believe in this formula, you've got to believe in this formula, because first of all, you get this formula by setting z equals 0. This line is a level curve of this plane at z equals 0, right? So that's obvious. That's obviously the case. But then if you believe in this, you also have to believe the fact that a and b, if you take these two coefficients, a and b, that this is a normal vector to this line. This is a normal vector to this line. Okay? ABC was a normal vector to the plane, a and b is a normal vector to the line. But now, my line here, my tangent line, which I'm trying to kind of explain that it's very important, is given by this formula, which is exactly like this formula, where this is a, and this is b, right? If so, then the corresponding vector AB is a normal vector to that line. And that's a gradient. So I have proved that this statement 1, that the gradient is a normal vector to the level curve. Okay? So there are two important vectors which show up when you have a graph of a function. One is a normal to the plane, to the entire tangent plane, and the other one is normal to the tangent line, to the level curve, which is a vector that is parallel to the floor, parallel to the xy plane. And there's a very simple connection between them. The first of them has three components because it's a vector in free space, which are fx, fy, and -1. And the second one is obtained from this one by chopping off this -1. And when you do that, what's left is just this one's going to, no, it's better, okay. All right. Hopefully it will survive the next 5 minutes. Okay, so let me repeat this for our worldwide viewing audience. We shouldn't forget them. This -1 is important, okay? The -1 is because the equation of the plane had, if we put z minus z0 to the same side of the equation, it will appear with coefficient -1. And that's exactly this -1 over there. Okay? And that's the z component of the normal vector. So you see the point is that the normal vector to the graph is like this. It's tilted. It's not like this. It's not parallel to the floor. It's tilted because the plane is tilted. But the normal vector to this line is going to be inside the same plane, which is the plane that is parallel to the floor. So therefore, it will be like this. What we do, we lose that -1. Well, here it appears like it's +1, but the reason lies, it's because, in fact, it is like this. It was like this. But if you think about the normal vector being like this, then you will see what I mean. Because think about that picture. So this is the, I feel like I'm waving my hands too much, but if you think about the normal vector as being on this side, which you can't see but can imagine, then you will see that its z component is -1. Okay? All right. Now hopefully we understand the geometry of this whole thing. So let's do a small. Let's do a small exercise. Let's do a small exercise. Suppose that f of xy is x cubed minus 4x squared y plus y squared. And the first question is to compute the directional derivative with respect to the vector u, which is 3/5 and 4/5 at the point 0, -1. So see, these are x0 and y0, and these are a and b. Let me call them. These are not the same a and b, though. Maybe not. Let me not use a and b now, because at the beginning I used a and b as components of the vector u, but now I'm using, in my later discussion, I was using a and b as components of the normal vector. So let's just not. Okay, so what do we need to do for this? Well, we need to find the gradient vector, because the directional derivative of f at this point is the dot product of the gradient at this point and the vector u. So u we are given, the vector u we are given, so we need to calculate the gradient vector. And the gradient vector consists of the two partial derivatives, right? So we need to calculate f sub x is equal to 3x squared minus 8y, and f sub y is minus 4x squared plus 2y, and then we calculate them at this point. So here we get 8, and here we get, yes? That's right, xy, thank you. I'm glad somebody's paying attention, that's good. So there's 0 actually here, right? This is 0, and second one I think I got, did I get it right? I got it right, so that's going to be -2, right? So the dot product is going to be between 0 and -2, and this one, which is 3/5 and 4/5. And by the way, note that this is indeed a unit vector. If you take this squared plus this squared, you'll get 1, right? So now we take the dot product, and the dot product is -8/5. So that's the answer for the rate of change or directional derivative in this direction. Now, another question which you will also encounter is the following: in which direction is the directional derivative does the directional derivative take the maximum possible value? Okay, and for this you have to find u for which this dot product will give you the maximum possible value. Right? You see, you cannot change this vector. This is a gradient vector. Once your point is given, this vector is fixed. But the direction you can travel any direction you want. So you can ask, given this vector, in which vector will give you the maximal possible dot product? Okay, and of course we know that the dot product is equal to the product of the lengths times the cosine. So to maximize the dot product, we have to maximize the cosine. And maximize cosine means the cosine is equal to 1, or -1 if you think in terms of the absolute values. And so that means that the vector, the direction vector, has to be the unit vector in the direction of the gradient. Okay, so that's how you solve this second part. Okay, I'm out of time, so we'll continue on Thursday.